Some of you might not even believe this, but still. Alright, so what we started last time was this pretty powerful notion, which is thinking of various problems we want to solve as optimization problems. Okay? And we saw several examples of this, where basically the idea was you have some problem, let's say it's some max independent set or something like this, and you try to phrase it as an optimization problem. Okay? And the way you do it is you introduce some variables that capture something about the solution, okay? Like whether some vertex is present in the independent set or not. And you define an objective function that you want to minimize or maximize. And you might have some constraints. You might have some constraint that says some variable is 0 or 1, something like this. And we saw a lot of examples last time. Like we saw this example of maximum independent set, where we basically had a linear objective, but the constraints basically said xi had to be 0 or 1. So that just captured which variable was in the independent set and which was not. And we saw that maximum flow naturally turns out to be what is called a linear program. So we said it's a natural optimization problem. And we saw that some problems it's not very easy to write them as optimization problems. Okay, and the standard example of this is the spanning tree. So if you guys remember, we could not write it as a compact. Or we said you could, but it takes more effort. So we needed this exponential sized set of constraints. Okay, we needed an exponentially many constraints to write the span. Okay, so alright, so this is what we saw last time. And so the other thing and formally this is what it was. So you have some variables xi. So this is what is an optimization problem. Okay, so you have variables x1 through xn, and you want to minimize or maximize some function f of x subject to some constraints. Think of constraints as being, they could be anything in principle. They could even be things like xi belongs to 0 or 1. Okay, so. And we said that you can usually view this in a geometric way. Okay, so you can look at set of all feasible solutions. Feasible x. Okay. And yeah, so this is basically a set of all x that satisfy all these constraints. Okay, so x in Rn that satisfy these constraints. And we saw some pictures of sets like this. So any questions about basic optimization? The formulation? Alright, so hopefully it's clear. Okay, so the other question we asked last time is, okay, so you can phrase a lot of problems as optimization, but when can you solve these problems, right? So there's no use phrasing a problem as optimization if you can't solve this optimization problem, right? And so one case which is usually called convex optimization is one in which your objective function, the f of x that is in this slide, is what we call convex. Okay, so the objective function is convex, and the feasible set is convex. And we define what that means. So a convex set is basically a region of, so this is a subset of R to the n, in which you have the property that if you take any two x and y in the set, the full line segment joining x and y lies in the set also. Okay, so we said this is an example of a convex set, but something like this is not, because if you take x and y here, some point on this segment does not lie in the convex. So this is not convex. Right? And a convex function, we said intuitively it's a function that kind of curves upwards. Okay, so it's something that looks like this. This is how a one variable convex function would look like. So this is the x. And we said that the general description of a convex function, the general property of a convex function is that if you take any two points x and y in your domain, okay, so these are just any two vectors x and y, then if you look at the weighted average of x and y and you look at f of that value, it's smaller than or equal to the weighted average of f of x and f of y. And I said, so this looks abstract, but one easy way to think about this is to set lambda equals half, okay, and say that f of x plus y by 2 is smaller than or equal to f of x plus f of y divided by 2. And geometrically this basically means you take any x and y here, okay. So this height is f of x, this height is f of y, and what we're saying is the f at the midpoint of x and y is x plus y divided by 2. The f value at this midpoint is smaller than or equal to f of x plus f of y by 2, okay, which is this. Okay, so that's why this captures this exact intuition that the curve kind of slopes upward. Okay, so the curve, yeah.
So another way to say this would be to say the area above the function is a convex set, right?
Exactly, yeah. So you could say that. So the area above is not very well defined. So what you say is you look at what are called level sets, which is the set of all points x such that f of x is less than or equal to some threshold tau. Okay, so let's call this L sub tau. Okay. And a function is convex if and only if L sub tau is a convex set for every tau. Okay, so this turns out to be equivalent. So is a convex set for all tau. Okay, so this is nice. So any questions about this alternate definition? So this is like saying I look at all x where f of x is less than or equal to this. Okay, so in this case it could be everything on this side of the x-axis, or maybe until this point. And this set is convex, right? Because it's just an interval. So this is an alternate way of defining this. Okay, so if you don't fully understand it, doesn't matter. Just think of a convex function as something that satisfies this. All right. So what we said before is convex optimization, where if you have a convex set and a convex function f, and you want to minimize it over a feasible set S which is convex. We said that this kind of optimization problems are typically easy. Okay? So not always, but these are easy in the sense that they can be solved in polynomial time. Okay, so this is the general template. I'm not making a formal statement here. So these are the sort of problems that are typically easy. Okay? So we'll give examples of this in a bit, but this is generally good to keep in mind. Okay? And we'll see a generic algorithm that usually works for these. So, see that. But first, so the important thing to notice is it's only minimizing a convex function. Okay? So if instead you wanted to maximize a convex function, it could be difficult, it be hard. So maybe we'll see an example of that in the homework. But maybe some of you are thinking minimizing f of x is the same as maximizing f of x is the same as minimizing minus f, right? So you could ask, okay, maybe f and minus f are both convex, right? So what would that mean? like suppose f of x and minus f are both convex, then what kind of function should f be? I guess some of you know the answer, but so you can easily deduce this. Okay, so what does it mean that both f and minus f are convex? Right, so in this case you will get that f of x plus y by 2 is smaller than or equal to f of x plus f of y by 2. And now if minus f is convex, you can use the same inequality for minus f. Okay, so you get that, so you get minus f of x plus y by 2 is less than equal to minus f plus minus y by 2, minus f y by 2. And this basically means that f of x plus y by 2 has to be equal to f of x plus f of y by 2. Okay, this is for all x, y in the domain. And this can only happen if f is linear. Okay, so under some minor assumptions like continuity and so on. So this means that f is linear. So the thing to remember is, if you have a linear function, then you can do both minimization and maximization over convex sets. But if you have just a convex function, then convex objective, then you can just minimize it over the convex. Okay, so this is something that good to remember, good to keep in mind. Okay. All right. So what is an algorithm? Right. So I said that this is typically easy. Okay. So which means you can solve it efficiently. And in some sense, the reason this special case is easy is because you can do some kind of local search. Okay. So what does this mean? So suppose I look. Suppose I have some convex function f. The goal is you want to minimize convex function f over a convex set S. Okay. So this is your goal, and let's say S is this set. Now consider the following very simple algorithm. Okay, so which is start with some x in S. Okay, and look around x. Okay, so try to improve x by moving in some direction. Okay, so how you find this is it depends, but you could say, okay, I look in a small radius around my point x. And I try to see if I can reduce the value of the function further. Okay. Try to see if going to some point on the boundary of this ball actually reduces the value of f of x. So is the algorithm clear? I look in a ball of radius around about delta. Think of delta as somewhat small. Okay. And I go to let's assume for now that you can do some kind of a search on this ball. Okay, so which means that you go to some neighboring point where f of x is smaller. Okay, so point y in the ball with a smaller f value, move to y. Okay, and keep doing this. Okay, so this, you can imagine you can do this by just perturbing x along various directions. Right? So this seems like something that you could do. Okay, so I'm being intentionally vague here. Okay, so this is something you can do, let's say. Now the claim is, if you can no longer make an improvement like this, then you're already almost at the minimum. Okay, so the claim is, if we cannot make an improvement, we are already at the okay. So basically, I mean, to be formal, you've got to say that if you cannot make an improvement, then the optimum point lies in a delta radius ball around your x. Okay. So that's the formal claim. So why would that? How would you prove such a statement? Not that we are just trying to say that, I mean, you know, basically local search works, right? So you explore locally around your point, and if you can't make an improvement, you declare that you are optimal. Okay? And we are saying that this simple algorithm is actually correct. Okay. So basically what you've got to argue is, suppose you get stuck at a point. Now, could there be a point somewhere far out? Okay, so x star, let's say, which actually has a f value that's much smaller than f of x.
You prove that if that is the case, then it's not convex, the function is not convex.
And how would you do that?
Well, everything around your first point, if you do a local search and can't find anything smaller, that means everything around your first point is bigger.
Yes.
And then the second point is lower than it, so.
Yeah, exactly. So that's basically the right intuition. So everybody see this intuition? So what he's saying is, if you just, let's say, I have this point x and I have this point x star. Okay. Let's forget about the whole space and just think of this line joining x and x star. Okay. So, and I zoom in on this line, this is this line. Now I know that f of x is something, f of x star is smaller. Okay. Now, how could it be that you increase at first and then drop? Right? So in this case, the function will not be convex, because if you increased, then and if you drop, then basically you get that. You lose convexity. Let me write a formal proof so that you know how to write a formal proof. Okay, so intuitively it is clear that you can't have a function that only curves slow. It only increases in a curved way, but yeah. So let's write it formally. Okay. So again, look at this line. Okay, look at this line segment that joins x and x star. And look at the point which is delta away from x. Okay. So let's call this point, any point on the line segment, you can write it as t times x plus 1 minus t times x star. Okay. So this is an observation we saw last time. Okay, so any point, let's call this point y can be written as some t times x plus 1 minus t times x star. And so what do we know from convexity? Right, so we know that f of y is smaller than or equal to t times f of x plus 1 minus t times f of y, f of x star. Okay, so this is what we know from convexity, right? So this is the definition of convexity. And now, so this can't be if f of y is bigger than both f of x and f of x star, right? So you can't have this equality. So what we are assuming is f of y is bigger than f of x, and f of x is actually bigger than f of x star, because x star was the minimizer. So is this clear? So x star is the minimizer, therefore we know that f of x star is less than or equal to f of x. And local search did not work, okay, so which means that f of y is bigger than f of x. Okay? And this is a contradiction, because the first inequality means that the right side, this implies that the right side is less than or equal to f of x, and the second inequality basically says f of y is strictly bigger, okay, and this can't be. So this is the formal proof of this intuitive argument that he said. Okay, so you can't increase and then decrease and then keep the function constant. this is basically that one. And this says that, so this proves this pretty nice and important observation about convex functions, which is that if you have any point which is a local minimum, okay, so any local minimum for a convex function is also the global minimum. And this is a very important fact about convex functions. Okay. And so what I glossed over here is I said that find a point y in the ball around this point which improves the function value, right? So how do you find that, go about finding that? For continuous functions, turns out there is this quantity called a gradient, and if you move in the opposite direction of the gradient, you will always reduce your function. Okay, so for those of you who know, this is just a concrete way of implementing the local search that I just mentioned before. Okay. And for those of you who don't bother. Okay, so that's if you know a little bit about gradient calculus, this is easy to see. Okay. So this just gives a concrete way of doing local search. So any questions about this local optimum, global optimum? Because this is a very important concept. Alright, so this was convex optimization, and this is a pretty general, powerful way of solving problems, right? So, but as I said before, so there's a lot of issues here which I didn't get into, which is how do you find the first feasible point, right? So that I didn't get into. Okay? And also, what should this delta be, right? So this is something that I didn't talk about. So can you move far, or do you have to, like, I mean, how do you pick this ball delta, I mean the radius of this ball delta? Okay, so is it okay to take long steps? And if you do, how long does it take to converge and so on? Okay, so in general it's hard to work these things out in generality, but you can do this for specific problems. Okay, so and that's kind of what we'll get at today. Okay, so we'll look at the specific case, which is called linear programming. So this is a special case of convex optimization where basically you have a linear objective and all the constraints are actually linear. Okay, so what does that mean? So this basically means you have, let me give an example here. So you have your objective basically looks like this. Let's say you have variables x1 through xn. Then your objective looks like this, and all your constraints look somewhat like this, right? So I've written this in a vector notation, but what this actually means is the constraint looks like a11 x1 plus a12 x2. So this is just the left side is a linear function, and you have less than equal to something. Okay, so this is what is called a linear constraint. So everyone clear on this? The notion of a linear constraint and a linear objective. Okay, so it's a natural thing. And so if you have this sort of a thing, because every linear constraint is a half space as we saw last time, the intersection of half spaces is again a convex set. So this is a special case of convex optimization. This is a special case. So, and this is one of the earliest cases of convex optimization that people study. Okay, so this was actually studied in the 50s by, I guess the first kind of write-up of this was due to Danzig. And he also came up with the first concrete algorithm for this, for solving problems of this kind. And there are a lot of problems in this area called operations research. We'll get to some examples in a bit, where basically you study problems of this kind. Okay, so where you have linear constraints and a linear object. And one of the big questions which spanned nearly like 3 decades, 50s to the 70s, was, can you solve linear programs in time which is polynomial in the input size? Okay? So it's the size that you take to write down the whole program. Right? So suppose I give you n constraints like this, or a bunch of constraints like this, then you take some space to write down the AIs. So if you remember, this is the kind of thing we've always been wanting to do. Right? So even for flows, we said we want algorithms that run in time that's polynomial in the space you take to write down the input. So the question is, can you do such a thing for linear programs? And this was not clear. For the longest time, people didn't know how to do this. And so a lot of research went into proving this. And it turns out that this Russian mathematician called Khachiyan came up with the first provably polynomial time algorithm for this. Okay, and I showed that it's polynomial in the input size. And it was also this very out there kind of an algorithm. Okay, so it was something that was completely unexpected, and it's what's called the ellipsoid algorithm. Okay, so how many of you have seen some form of the description of the ellipsoid algorithm? Okay, so we won't cover it in this class, but I can put up a link to this. Okay, so it's actually very beautiful, very unexpected kind of an algorithm. Okay. And it turns out, so this was. This was the height of the Cold War, so apparently this was not taken very well by the American mathematicians, because the Russians got there first, and this was some optimization analog of Sputnik. Okay, so there was a lot of uproar about this, and there's a lot of controversy also about how in practice this algorithm is actually slower than what these guys had invented and so forth. Okay, there's a lot of arguments at the time, as you would imagine. Alright, but the bottom line is that you can solve linear programs in time that's polynomial in the input size. And it's by this very beautiful algorithm called the ellipsoid algorithm. So, alright, so as I said, we won't do ellipsoid, but we'll see one of the easier algorithms for solving linear programs. And so the key to what is called the simplex method is a geometric view of linear programming. So this is something that is very useful even though you don't solve the problem this way. And the idea is, as we said before, every constraint is a half space. Right, so it cuts off half of the plane. So a constraint of this form is basically you have n-dimensional space, and then every point on one side of this half space of this plane satisfies this constraint, and no point on the other side satisfies this. Okay, so this is what we mean by a half space. So we have this, so this is one constraint. So this is A1 transpose x less than equal to B1. Then you have another constraint which is probably like this, and so on. So note that the feasible set need not be finite. Okay, so for instance, if you just had one constraint, it only says that all your feasible points must lie on one side of this plane. Okay, so they could be arbitrarily far away. Okay, so this is something to keep in mind. But in general, the feasible set is some intersection of half spaces. And an intersection of half spaces is usually called a polytope. Okay, so this is it's just a name. It could be finite, it could be infinite. Okay, so it's finite if you have constraints that fully close this thing. So you have a polytope that looks like this, and what you want to do is you want to minimize some linear function on it, right? So let's say your linear function, so this is the x1 axis, this is the x2 axis. So I guess I have a slide just for you. Yeah. So let's see an example of this. But a linear function basically tries to find a point in this polytope. Okay, so the polytope maybe looks like this, and you want to find some point x on this polytope which maximizes some linear function, right? And we'll see how such a point should look like. So let's do a 2D example first, so that all of you are clear with what a polytope is. Okay, so any questions about this general definition in high dimension? So it's basically, in high dimensions, don't try to visualize it, just think of it as an intersection of half spaces. Okay, so you can, and that's about the best description one can give. Okay, so let's see in 2 and 3 dimensions what this kind of an object looks like. So 2 dimensions, let's say you just have variables x1 and x2, and you have the plane which is suppose you have very simple constraints. Okay, so I'm going to write constraints like x1 plus x2 is bigger than or equal to 0, and x1 less than or equal to 4, x2 less than or equal to 3. So this is just a very simple set of constraints. And what does it mean? So it means that you have how does x1 less than or equal to 4 look like? Okay, so it's in the right direction. Yeah, so x1 less than or equal to 4 basically looks like you have x1 equals 4 and everything on the left of this. And so it involves all the negative points and so forth. And x2 less than or equal to 3 looks like this, everything on this side. So the feasible set of both of these is you have this point and everything to the left of this. Okay, so this is actually an infinite set if you just had these 2 constraints. Okay. And now you have the third constraint, x1 plus x2 bigger than or equal to 0. How does that look like?
Through the origin.
Yeah, it goes through the origin and it looks, I guess it's at a 45-degree angle. It looks like this. So these 3 constraints just define this big triangle. Okay, so I guess it looks like this. So this is the feasible set for these 3 constraints. And in a 2-dimension, a polytope is just either a convex polygon or some infinite region. Okay, so it could just be, for instance, when we didn't have this constraint, we just had an infinite region which went like this. Right? So in 2D, a polytope is just either a convex polygon or some infinite region whose boundary is gone. And now what we want to do is the kind of problems we want to solve is maximize, let's say 2x minus 3 or 2x1 minus 3x2 over this set. So we are trying to solve pretty simple problems like this. Okay? So what would the maximum for this be, just looking from the picture? I mean, can you tell? I mean, so what we want is for some point here, you want to compute 2x1 minus 3x2. Right? So that's the value of the function. So the f is simply 2x1 minus 3x2. And you want to find a point that minimizes this. Oh no, sorry, maximizes this. Okay, so since it's a linear function, it doesn't matter if you minimize or maximize. So
Like x2 has to be negative.
Yeah, so this function, it basically, if you want to maximize it, somehow the slope of this looks, I guess, like this. So you would want to go in this direction, right? Or yeah, so in the direction of negative x2 and positive x1, right? That's the direction that maximizes this function. Okay. So if you think about this a little bit, so you'll get that you want to ultimately be, this is the origin, okay, so, and you, yeah, I would say work out this example. It's, but what you will find is that you will want to be in some direction that looks like this. And now you try to find an extreme point in this direction, and you will essentially find that this vertex is the best vertex to be. That this vertex is the best of the feasible points in terms of this optimization. Okay. So you can try to work out a few examples, and what you will always find is that so if you look at the point that attains the maximum or the minimum of any linear function, so it will always be a corner point, it will always be a vertex of this polytope. Okay. So this is the second, this is the other main thing about linear optimization, which is that if you take any point x that attains the minimum, okay, so it's always a corner point for this feasible polytope. And the cool thing is that, if you think about it, the polytope is just the feasible set, right? So this has nothing to do with the objective function. Okay, so the objective function could be anything, and the minimum is always attained at a corner point of this polytope. So this is pretty nice because the polytope is just some kind of a finite object. In this case, it has only three corner points, right? But what this is saying is that any linear function in two dimensions, there are infinitely many of them, will be minimized or maximized at only one of these 3 points. So it's nice to know, although it's, after you think about it a little bit, you expect this to be true, but still it's good to know. There are lots of functions, but they are all optimized at one of these extreme points. So if you could list out all these extreme points, then for any linear function, one of them will have to be the minimizer, right? So this could be one way of solving this problem. Okay, so suppose you want to minimize or maximize a linear function, you just compute all these corner points of this polytope, and you can try to minimize your function over this. Okay. But it turns out, this is correct, but it turns out this is an exponential time arrow. This could take exponential time because the number of vertices, even if you defined your polytope using only like a small number of constraints, the number of corner points could be exponential. Okay. So this is one example we'll see in the homeworks where the polytope will be defined by a few constraints, but the number of corner points will be exponential. Okay, so you can't just use this basic. So these are very easy to construct.
So that will depend on the number of dimensions also.
Exactly. So if the number of dimensions is relatively small, then you can show this is always polynomial. Like if if you're in 2D, you can't have, if you have n constraints, you can't have much more than n corner points. Okay, so in 2D, this kind of simple algorithm works. And usually, if you have the dimension being, actually, let's use consistent notation. So if your dimension is n and number of constraints is n. I think I might be a little bit wrong on this, but maybe Wyman can correct me. So this is m to the n minus 1 by 2. This is the number of corner points you can have, or maybe n by 2. N by 2 floor or something like this. Right? This is the number of corner points that a polytope in n dimensions can have. Okay. So Is this right? Something like this, right? So I don't remember if it was -1 by 2 or just by 2. So, yeah.
If your objective, I guess, minimizes along the line, I mean, like negative x minus x2, or
Yeah.
there's 3 different ones obviously here.
Yeah.
So that's not at a corner of the polytope, but
Well, there could be many optima, if that's what you're saying, but at least one of them will be at the corner.
okay.
Okay. So if you could have cases where, let's say, you want to maximize in this direction, let's say, okay, maximize just x2. Okay. So then any point on this top line will actually be fine, and it will attain the maximum. But there's always some corner point which also attains the maximum. Yeah, that's a good point. So any other questions? These are all good questions. All right. So yeah. So this is in some sense the main idea behind the simplex algorithm. Okay. So that the point that attains the minimum is always a corner point, and searching over corner points could be very expensive. So you need some kind of a faster algorithm to search over these corner points. Okay, and this is exactly what the simplex algorithm does. And in some sense, you don't want to keep track of all the corner points, right? So because there are exponentially many of them. And in some sense, so the simplex algorithm does something which you would naturally expect it to do. What it does is it starts at some corner point. Then it tries to jump from one corner point to the other. So if you have in 2D, this is very easy to imagine. So if you have a polytope that just looks like this, so in this case, every corner point has 2 adjacent ones. And what you could think of doing to minimize or maximize the function is you start at any point. Okay. How you find this first point is a tricky thing. Okay. So let's not get into that. Okay. So suppose you find some corner point. So in practice, this turns out to be easy to do. Okay. So in practice, finding some feasible solution is usually easy. So that's why this algorithm became very popular. That you find some feasible solution, and from there you kind of do this kind of an algorithm. Okay, so you move either to one side or to the other, and at every step you only improve the objective value. Okay, so if you have a minimization problem, you just decrease the value of this, and you keep doing this. And you stop when you get stuck. Okay, so when moving to a neighbor always results in a worse objective value. And so this is essentially like local search, but you're doing local search on the vertices of this polytope, right? So there are a bunch of questions you've got to ask, right? So we won't go into the details of this because going into the details requires a lot of tedious calculation. Okay, so I'll point you to these things, but you don't need to know the details. Is my point. Okay. So, but the idea is. So first thing to know is how do you find a starting vertex? And usually the way people do it is finding a vertex is difficult. So what they do is they find some interior point, okay, some feasible point, and then you try to move to the corner along some direction. Okay, then you will hit one corner, and then you just keep along that corner, and then you try to move. Okay. And and then you'll hit something that's actually a corner. Okay, and there's ways to formalize this, but I won't get into it. So you can usually find a good starting vertex pretty efficiently. Okay, so if you found some feasible point, you can find a starting vertex. Okay. And once you do this, so in 2D, the picture is actually very simple, right? So at every point you only can go in two different directions, right? So it turns out in n dimensions it's not much more complicated. You usually just have n different directions to move along. Okay? So even though there are exponentially many corner points, the number of adjacent corner points is actually pretty small. Okay? So this is something you can prove. Okay? So it's just polynomial in the number of constraints you have. Yeah?
Why can't we say any diagonal starting?
What do you mean?
Take any vertex and you start.
Yeah, so how do you find one vertex, right? So all you are given is a bunch of constraints. Okay, so if you are given a bunch of constraints, finding one vertex. So you could say a vertex, actually this is something that is good to know. So any vertex of this polytope is defined by d of the if you are in n dimensions, n of the constraints becoming equalities. Okay, so that's what defines one vertex. As you would imagine, right? Because you have n-dimensional things, you need n equations to find one point, right? So that's how you find one vertex. But not every vertex you get like this is actually feasible. Okay, and sometimes you might have to. I mean, your constraints could be such that you have constraints like this. And then you have another constraint which chops off this corner point. Okay, so your feasible set is only this. Okay. So if you try to find a vertex by just taking the intersection of these two lines, then that's not a valid vertex, okay, because that's not feasible. Okay. So in general, it's tricky to find the starting vertex. Okay. And you have to do a little bit of work, but it can be done. And the other thing is there are many possibilities to move. And as I said before, in high dimensions you could move even in 2 dimensions. Both your solutions, both the neighbors could yield in a better function value. Right? In this case, so you can imagine an extreme example where your optimum is somewhere over here, let's say, and then you have a long path here which also leads to the optimum. Your objective function could be something where both these will end up in improving this thing, so you could end up taking a really long path. So how do you avoid that is something that's also an interesting research question. This is something that people study. And we don't know of very good ways of doing this. Yeah?
Can you explain this better?
Yeah. So what I said is, so suppose you have a polygon, right? So in 2 dimensions, let's say you have a polygon like this. Okay. Now let me draw a slightly better figure. So imagine this. Imagine this is your objective function. Okay. So the objective function basically says find a corner point along that direction. And so that means this is the optimum point. Right? So now let's say you are here. Okay, so this is your starting vertex x. Now this, if you go along that path has length 3. Okay? So if you do 3 iterations, you'll end up finding the optimum point. Now you could also have a very long path in which you always improve the objective, but it takes way longer to get there. Okay? And in 2 dimensions it's not so bad because the total number of corner points is only small. But in n dimensions, if you keep making wrong choices, you will still get to the optimum, but you could take exponentially long to get to the optimum. Yeah.
What if we parallelly take 2 paths which are like, so whichever finds something.
You can try to do breadth first search on this. Okay, so that's what I'm getting to. Okay, so basically you can do breadth first search on this, and try to see if you can reach this point. But actually before that, so another thing that people do which works well in practice is they just go to the neighboring vertex that improves the value the most. Okay, so this is the most natural thing to do. This usually works well, okay, although there are some bad cases for it.
If you do breadth search, you need to know the optimum vertex to begin with. So
No, you keep finding vertices one next to the other. So suppose you have,
and keep track of improvements.
so that's the thing, if you don't keep track of it, you will have to potentially end up storing all the vertices, which is exponential space. Okay, so that is not feasible. But even if you could do it, it's not clear how many steps it takes. Okay, so this is one of these, this is actually a big open problem, which is, suppose you have n dimensions and you have m hyperplanes that define your feasible set. Okay, so you have m constraints, m linear constraints, and you have n dimensions. This is the setting in which I said that there are m to the n over 2 possible vertices. Right? So this is the same setup. And the question is, if I take any two vertices, does there always exist a short path between them? Okay, so is the question clear? So I'm not even interested in finding this, right? So does there always exist a short path? Okay, a path of length, let's say m times n. We don't know the answer to this. Okay, so this is one of the big open problems in this area called combinatorial geometry. So we don't know if you can come up with a polynomial time bound like this. Okay. And it's what's called the Hirsch conjecture. And until very recently, people thought, okay, it could be as small as m minus n. Okay, so and people didn't know that it couldn't be any bigger. Recently, somebody came up with an example where the diameter is a little bit bigger than this, okay, but it's only a little bit. It's like 2 times. Okay. So this is one of these big open problems that no one has any good approach for. Yeah, so I put it up here just to tell you that sometimes very simple questions like this, no one knows how to reason about them. Alright, so this is what's called the Hirsch conjecture. So for all you know, it could be possible that you can always go from one point to the other quickly, but we don't know good ways. Okay, and this is the main problem with the simplex algorithm, that we don't know if you can bound the running time in a polynomial. Okay, because if you can, then you would end up answering that question. And yeah, so I was going to tell you, okay. So I was going to prove this one thing. I won't prove it, but I'll just write down the statement, okay, so that it's clear for everyone. That simplex algorithm always converges always finds optimum solution, right? Because this is for the same reason that local search always works. So you have to be a little bit more tricky because you don't move to a neighbor, you move to a neighboring vertex. Okay, so you have to be a little more tricky. That's why I wanted to have a proof, but let's not get there. Okay, but you can actually extend the kind of analysis we did before to say that you actually always find the true solution. But another point to remember is we don't know if it's polytime. And the question which you should ask yourself is, just some time ago we saw a generic algorithm for convex optimization, right, which basically looked at a point, tried to move to some neighboring point. And that was doing some kind of a continuous search, right? So what that algorithm would do is, if you want to minimize or maximize some function, it would start somewhere, maybe it starts at a corner, then it would move inside internally and try to move towards the optimum, right? So this is what that searching in a ball of radius delta type algorithm did. But now what we're suggesting is you just keep jumping to vertices. Okay? And I'm saying that this is the preferred method of solving linear programs, right? So any guesses on why that could be the case?
The amount of space required.
Well, that's not so much, right? Because here also you have to maintain the state, which usually involves maintaining a set of constraints, which this vertex is satisfying.
But there's no, you don't have to choose that small amount by which you need to move it.
Yeah, so you don't have to, so that's always there. Okay, so you don't know how much to move, so, right, so it's not clear. So maybe you have to move and then search, and then basically check for feasibility every time and so on. So there's a small notion of efficiency there. But perhaps the biggest reason people use this in practice is because you hope that the number of iterations is way smaller. Okay, and this turns out to be true in basically all applications. Jumping to corner points ends up making much more significant progress than doing these small steps. Okay. And in some sense, all these ellipsoid methods and all these provable methods, not all, but many of them go through what is called this interior point of the polytope. Okay, so that's why, so this is this trade-off I was talking about. That for some of these methods, you can actually prove that you converge in polynomial time, but in practice, this simple jumping along the corners algorithm usually does pretty well. Okay. So
It also depends. In practice, you might not have very high dimension.
Right. So, but this is true even in fairly high dimensional problems. Alright, so let's, so these are some comments that I wanted to make. And yeah, as I said, this part of the course, I want you guys to get a sense of what's going on rather than the full details. That's why I'm not going into the details of simplex algorithm. Okay, because, yeah.
So how will we get to know the set of these points? Like that would again take exponential space, right?
So every vertex has only a small number of neighbors. And that goes back to the observation I made when someone asked a question, which is that every vertex is defined by n of the inequalities. Right? So if you are in n-dimensional space, n different inequalities, if they become equality, then they will find a unique point. Right? So every vertex you can actually think of it as corresponding to n different inequalities. And now, a neighboring vertex is one in which n minus 1 of these inequalities remain the same. The nth one is different. Okay? So you change one of these inequalities. So that's how you would define a neighbor. And in this way, you basically have only a small number of neighbors by definition. And yeah, and this corresponds to the geometric notion of neighbor, where you walk along one of these. So all these statements are intuitively pretty easy to see, but to prove them we actually require some work. Okay, so that's why I'm not doing it. And yeah, so the takeaways from this are, it's a pretty fast algorithm in practice. If you don't know if it's in polytime, there are lots of packages that implement this also. Alright. So before so the next time we'll see a powerful notion related to linear programs called duality. But today I wanted to talk about some applications of linear programs. Okay. And in particular, so one thing I mentioned at the beginning is the original motivations, right? So these are the motivations that existed from the 50s, which is that linear programs can directly capture things like flow problems. Okay, so we saw that max flow can be captured using linear programs, and anything that can be captured using flow can therefore be captured, right? But there are a lot of other network optimization problems. Okay, so things about communication networks and so forth, which you can actually easily capture using linear programs. Okay? And the same is true for things like routing in networks and so forth. Okay, so we'll see one example of that. So in general, if you have a problem where you have continuous parameters, okay, so you just have variables that are allowed to take any real values, and you have some constraints on them and you want to optimize them, then linear programming is a great way to do this. Right? And so for this, I actually, on the course webpage, you can find a link to the survey by Danzig. So he's in some sense the father of linear programming. So he came up with the Simplex algorithm and so forth. So he has a survey like looking back. It was written in the 90s, I guess. Okay. So it's a pretty nice to read the historical context of this. Okay. So for continuous optimization problems, this kind of an LB framework is very natural and it's pretty useful. But a more recent development, which is rather surprising, is how to use linear programming for what's called discrete problems. Okay. So this is an example. So let's say we have, So what is a discrete problem? Right. So these are problems like independent set, things like this. These are basically combinatorial problems, okay, where the object you want to pick, which you want to select, is some combinatorial object. Okay, so like max independent set. So here you have a graph and you want to pick some vertices so that no two of them have an edge. Right? So this is the maximum independent set problem. And the way we wrote this as an optimization problem is each xi belong to 0, 1. And you had for all edges xi plus xj is less than or equal to 1. Well, ij is an edge, we said xi plus xj less than or equal to 1 because both of them cannot be in the independent set. Okay, so this was the reasoning we saw last time. And we wanted to maximize sum over I xi. So if you didn't have this constraint, okay, so then this is just a linear program, right? Or if you just had a constraint 0 less than or equal to xi less than or equal to 1, then this is a linear program. Okay? But because of this actually is not linear. I mean, it's not convex even, so we couldn't quite solve it. So the kind of questions we'll ask today are, can you use linear programs even to solve problems where you seem to have this kind of integrality constraint? So where you seem to have this. So another example is what's called max bipartite matching. So this we've seen last time. So this is the problem that you guys saw in the homework and so forth. So you have a bunch of vertices and you have some weighted edges, and you want to find some matching of maximum weight. Okay? So matching is basically every vertex goes to at most 1. And this sort of thing you can write using a linear program, because you could say, you could think of a matching as just collection of edges, right? So maybe you pick this edge and this edge and this edge, and you could have a variable xij for every edge. And xij 0 means that edge was not picked. Xij is 1 means that edge was picked, which means I was mapped to j. So this is a natural way of doing matching. And you can come up with constraints that have to be satisfied. Okay, so actually, what would you guess are the constraints that have to be satisfied if you define matching this way? I mean, apart from, let's say, xij is in 0, 1. So what is a constraint that you would need for matching? Yeah.
So you want the sum of all the edges that touch any vertex to be 1 or less.
Exactly. Right. So this is the natural constraint. So for matching, you would have xij for all edges. These are the variables. And the constraints, first you have this xij belongs to 0, 1. And then you have sum over, for every I, for every vertex I. So you have sum over j in the neighborhood of I. So gamma of I is the standard symbol in graphs which denotes the neighborhood of I. So of I, xij is less than or equal to 1. So this is true for both the left side and the right side. For every vertex. Okay. And now, so what's the objective? Maximize the weighted matching, right? So if you picked an edge, you get a value wij, and otherwise you get 0. So the maximum is just sum over ij, edges ij. So a couple of things about this. Okay. So one thing to notice, which is actually rather cool, is that so as I said before, the polytope is defined only by the constraints, right? The objective has nothing to do with it. So, but note that these weights on the edges only show up in your objective. And this is one very nice thing about this kind of linear programming approach to matching, where basically the polytope is independent of the weights, while your objective is the only thing that depends on the weights. Okay? So in some sense what this says is weighted matching is almost as difficult as is as difficult as unweighted matching. Okay? And this is something which is if you guys have seen flows, so flows could capture unweighted matching but not weighted matching. So that was that was one thing we saw. But this kind of framework doesn't distinguish between weighted and unweighted things. Okay. So this is just for people who think about these things. It's so that's the usual advantage of linear programming type methods, that you can capture weighted versions of problems much more easily than unweighted versions. Okay. So that is more for people who do research on this. Okay, so this is one point. The other thing is, we still haven't gotten rid of this, right? So this is still not quite a linear program. Why?
Because you have an acceleration belongs to
Yes, so we have these main constraints, right? So this is not quite linear. So what you could ask is, okay, so suppose I replace these constraints with 0 less than equal to xij less than equal to 1. Okay. So, and now this is a linear program, right? So now these are linear constraints. These are just constraints that look like boxes, and you're asking, and you have a bunch of other linear constraints, and you want to maximize this this linear function of the xi. So everyone clear? So now this is a linear program. What you could ask is, so suppose you solve this linear program, can you end up getting, so what's the problem, right? So suppose you want to solve the maximum matching problem, and you solve this linear program. So how could a solution to this look like? Like, I'm not enforcing that the xi's are either 0 or 1, right? So for all you know, they could be fractional. So this is usually the problem with solving combinatorial problems via linear programs. Okay, so if you solve combinatorial problems like matching and so forth, you need this kind of an integrality constraint. But if you just replace it by this xi belong to 0 or 1, there's no guarantee that you always get an integer point, right? So what does it mean you don't get an integer point? It basically means that your solution, like a very simplistic case, could be you have 3 vertices. And you could have, let's say, the xij values could be half and half for this. And this satisfies the constraint because the sum of these two is less than or equal to 1. And you could have, let's say, like the same thing going on with this, and maybe the same thing going on with these two, right? So you could just have half-half for all these edges. And this solution is clearly not a matching, right? Because matching requires only one edge to be picked. So, but this is what's called a fractional matching. So you can still, it still satisfies all these constraints, all these linear constraints. It's just not a true matching. Okay? But in the case of maximum matching, turns out that there is always, so the theorem, this is actually a somewhat non-trivial theorem. It's not very difficult, but somewhat non-trivial. Is that for maximum matching, for max bipartite matching, all the vertices of this polytope are actually integral. So is the statement clear? So what this is saying is, you look at this polytope, which is just defined by this constraint and this constraint. So these are just linear constraints, right? And they look like this somewhat. And what this theorem is saying is that okay, so any point inside this polytope could be fractional, right? Because this is just a convex set, and there are lots of fractional points inside this. But the theorem says that every corner point of this polytope has only integer coordinates. Okay. And this is a pretty surprising thing if you haven't seen it before, because why would you expect every corner point to be integer, right? And this is why you can solve max bipartite matching using linear programming, because you know that every corner point is integral. And you always just find corner points when you solve using the simplex method or most other methods. So this is why when you solve it, you actually end up getting a corner point which is actually an integer point. So we won't prove this theorem, but this is a very special theorem in the sense that it is not true for many problems. It happens to be true for maximum matching. Okay. So questions about this? This is a very powerful concept that all vertices are integers, right? So how would you go about proving such a thing?
Is it because your ranges are all integers on the constraints?
It's partially because of that, yeah. So but that's not a sufficient constraint in the sense that for, let's say, independent set, if you try to do the same thing, you will end up, even there, your right sides and coefficients are all integers, right? But that cannot have this property because independent set is NP hard. Yeah. So yeah, it turns out this is non-trivial, and one way to prove this is to say, yeah. So let's not go into this, but I can point you to some very beautiful proofs of this. It's actually tricky how you prove statements like this. Right? But is the statement clear? Okay. Let's move on. So the next thing, which I was hoping to play, but I probably won't have time, is what is called rounding. Okay. So there are many problems, as I said, where it's not so nice as maximum matching. Okay. So let's look at this independent set problem. Right. So again, let's go back to independent set. So here you just have the constraints that actually you have constraints like xi belong to 0, 1 and xi plus xj is less than or equal to 1 for all ij being an edge, and you want to maximize xi. Okay. So this is an independent set. Now you could have a trivial solution to independent set to this linear program. So suppose you forget about these constraints and just make it 0 less than or equal to xi less than or equal to 1. Then you have a trivial constraint to this, trivial solution. Any guesses what this trivial solution is? Like, what is an easy way to get a pretty large objective value and still satisfy the constraint the 0 less than or equal to xi less than or equal to 1, and for every edge xi plus xj is less than or equal to 1. So I just have a graph. I want xi plus xj less than or equal to 1. So I have variables for every vertex. Right? So can I always make this objective at least n by 2? So exactly. So you can just set every variable equal to half. Okay, so you can set every xi equals half, and you're done, right? Because no constraint could be violated. So because xi plus xj is always less than 2. And so this is a trivial solution. This is and as you can see, this is a pretty bad thing, right? So even if your graph was the complete graph, okay, in a complete graph, what's the size of the maximum independent set? The complete graph means every edge exists. Okay, so what could be the size of a maximum independent set? It's 1, right? Because if you take any two vertices, they have an edge between them. So both of them could not be in the independent set. So for a complete graph, the true solution, true optimum is actually 1, while LP still has a solution of cost n by 2. Okay, so this is pretty bad, right? N is huge, and so the LP is far off by a huge factor. So in such cases, you don't expect to do anything. But there are many problems in which the LP solution is pretty indicative of what the actual optimum solution is. Okay, so the variables, so you try to solve this problem by just replacing these 0, 1 variables by just 0 less than or equal to xi less than or equal to 1, and you get something that's close to integral. So this is what, maybe we'll see an example of this in the next class, and this process is called rounding. Okay, so where maybe if you get a variable that's 0.9 and some variable that's 0.01, then you expect to make this 0 and this 1. Right? So this is what's called rounding, and it turns out to be a powerful thing. So we'll see.
Cool. So we did it right.
Nice.
All my classes, so you're not in them.
You did that, I didn't do it. I had to find my plan.